So in this lesson, we're going to learn how to use a balanced chemical equation to give you information on how much product you can possibly make from a certain amount of starting materials, the reactants, or variations of the theme. For example, figuring out how much reactant you need to make a certain amount of product. Now, before we begin this, it's imperative that you understand the mole concept, right? That a mole is just a number, a group of things. We count things in groups called the mole, and that group of things or set of things happens to be a huge number of them, 6.022 times 10 to the 23rd things or entities, and the things that we count in chemistry, right, are molecules, formula units, atoms, ions, a variety of things. So you need to know that. And second of all, you also need to know and be able to apply the concept of the molar mass. So the molar mass is, if you count out 1 mole of things, what is the mass of it, right, which you can calculate. So with that in hand, let's go ahead and proceed with the lesson. So we're going to study stoichiometry. Stoichiometry, the name, stoichion comes from the Greek meaning element and metron, meaning to measure. So we're measuring amounts of things. In general, when you're looking at any stoichiometry problem, the strategy for solving them, right, is represented here. We see that often what we need to do is convert from the mass of something to a mole of something. So we need a tool for doing that, and the tool is the molar mass. So that's one thing that you need to know and how to use it. The only thing that's new here to stoichiometry is the information of the balanced chemical equation, right? So, for example, in this equation right here, it's specifying that we require X moles of A, that when X moles of A are consumed, we create Y moles of B. So if we wanted to figure out how many moles of B we would form from a certain amount of mass of A, what we would do, we would take the mass of A, convert it to moles, so that now we can use our balanced chemical equation, and this mole to mole ratio, right, X to Y, presents the information that we need to link to go from here to here. So that's the new concept. And then finally, we use our old tool, again, the molar mass, but now we're talking about B, so we use it to generate mass of B if the problem requires us to do it. So it's important that as you're doing these problems, not to memorize recipes for a given problem to give you the answer. Instead, what you should remember are these two tools, right? The molar mass tool and the balanced chemical equation, the mole-to-mole ratio, to allow you to do the mole-to-mole conversion. So the mole-to-mole conversion is a second tool. Applying these two tools, if you know how to use them, you can solve any chemical stoichiometry problem that's given to you. A second thing that you need to know is the limiting reactant concept. So we're going to start off by focusing on strategy 1, just the mole-to-mole conversion and the mass-to-mole or mole-to-mass conversion. So in this particular problem, we have a balanced chemical equation describing the reaction between lithium hydroxide and carbon dioxide to form lithium carbonate and water. And there's significant interest in this reaction to use lithium hydroxide in closed cycle rebreathing units. So these are units that you could strap on your back and use for scuba diving, where you don't want any bubbles to be released, for example. Navy SEALs use them, as well as using them in a closed cycle rebreather up in the space station or in space vehicles. So basically the way it works is that when you exhale your breath, with the exhaled air, which contains a large amount of carbon dioxide, right, is passed through a canister that contains the lithium hydroxide. The lithium hydroxide reacts with the CO2, removing it from the gas stream to form lithium carbonate. So that removes the CO2 so that you can rebreathe the air again. To replenish the oxygen that's been removed, you simply have to add a little bit from a separate canister. The one thing that's nice about lithium hydroxide, if you note that all three elements are among the lighter elements in the periodic table, so this means that it doesn't cost nearly as much as some other CO2 adsorbents would if you want to transport this material up into space. Now, in this particular problem, you're asked to figure out how much CO2 will react with 1 gram of lithium hydroxide. So, where do we need to start in our thinking here, right? Before you get out your calculator, it's best if you figure out a map of how to solve your problem using our two tools, right? The molar mass as well as the mole-to-mole conversion, the number ratios that we have in our balanced chemical equation. So we're given the mass of lithium hydroxide, 1 gram. We need to figure out the mass of CO2 that reacts with it. So what we need to do then is convert our mass of lithium hydroxide to moles of lithium hydroxide, because that's the only way we can use the number relationships here in our balanced chemical equation. Now in step 2, we recognize that for every 2 moles of lithium hydroxide that react, we need exactly 1 mole of CO2. So we see our balanced chemical equation really as a recipe for understanding how things react in a number basis, not a mass basis. So we need to use that information here, right? The moles of lithium hydroxide, we need 2 moles of that for every mole of CO2 consumed. And then in the final step, we use the molar mass of carbon dioxide. So we're going to need our molar masses for lithium hydroxide and carbon dioxide. All right, we calculate them in the usual fashion. For every mole of lithium hydroxide as a formula unit, we recognize we're going to have a mole of lithium, a mole of oxygen atoms, and a mole of hydrogen atoms, and they weigh, respectively, these values, which we can look up in the periodic table. All right, now, we're going to look at these calculations stepwise. We're going to do this step first, then we're going to look at this step, and then we're going to look at this step, and then in the end, we're going to show you a way to combine all 3 steps in one calculation. So for the first step, that's the mass to mole conversion. We take our mass of lithium hydroxide, 1 gram, right? And write our molar mass in a way that the mass of lithium hydroxide can't cancel, so that has to be in the denominator, right? And our 1 mole of lithium hydroxide up top. And so now we've done our mass to mole conversion. We don't round our number here yet because we're going to be using this later, so we simply report where the uncertainty is as an underline, right? We have 3 significant figures here, so we report this value. We would round it to 0.0418 if we were finished. So now at this point we take our moles of lithium hydroxide, we do the mole-to-mole conversion. Where do we get this information? From the balanced chemical equation, right? You go back and look at the previous slide, it'll show you that for every 2 moles of lithium hydroxide that react, we need 1 mole of CO2 to do it. So at this point, we had a gram of lithium hydroxide and we showed that it will react completely with exactly 0.02088 moles of CO2. Now to get the mass of CO2 in the third step, we need to know the molar mass of CO2. We calculated that on the previous slide. And so now we have shown that for 1.00 grams of lithium hydroxide, it will react with 0.919 grams of CO2 when we round this off. So as I mentioned earlier, we've done this stepwise to focus on the individual steps and illustrating how we're using our 2 tools, right? The molar mass and the mole-to-mole conversion in the balanced chemical equation. We can string all 3 of these together. In fact, this is what you want to do on your exams and in your homework. And before you ever get out your calculator, you want to write all of this stuff out. Right? We're going to take our three conversion factors and link them all together. Here's the first one, the molar mass. Then we multiply by the second conversion factor, which gives us our mole-to-mole conversion. And then in the third conversion factor, we convert our moles of CO2 to mass of CO2. Note that all of our units cancels, and we end up with 0.919 grams of CO2. So now at this point, you would get out your calculator, and you type in 1 divided by 23.949. You take that value, divide by 2, and multiply by 44.01. You'll get your value here, and then you round it to 3 significant figures. All right, go ahead and take a moment, pause the video, and see if you can't solve this problem on your own. All right, just in case if you need a little hint on how to think about this, look at what the question's asking. How many grams of aluminum sulfate, that's this stuff here, is produced from 2.6 moles of sulfuric acid here, all right, in the following unbalanced equation? Well, first of all, you're going to have to balance it, right? So one thing that's useful when you see polyatomic ions, right? A polyatomic ion is a molecular species, so the atoms are stuck together. They're not separate. And so if you identify them, it makes sense to just count them as a single unit, right? So we see 1 sulfate unit here. We see 3 sulfate units here. So this really simplifies the balancing because we recognize that we need 3 sulfates on the side. So we put a 3 here. And once we've done that, we can see that, well, aluminum's already balanced, our sulfates are balanced. The remaining oxygen, right, is here in water and here. So we need 3 oxygen atoms to be balanced here. So we can put a 3 here to balance that oxygen, and hydrogen will also be balanced as well. So we have 6 on this side and 6 on this side. So it's already balanced. All right, so having done that, we'll give you a hint on how to start to think about solving this problem. First of all, if you think you need to take your moles of sulfuric acid and calculate grams of sulfuric acid, you're not thinking about this problem correctly. You're going in the wrong direction. Go ahead and generate a solution map first, right? Here's the general procedure, right? The mass to mole to mole to mass conversion. Where do you need to start in the sequence? This is where we want to end up, right? And this is where our information is. So we begin here, and we want to go in this direction. If you go in this direction, you're going the wrong way, and you're clearly confused about what you're doing. That's why this is helpful to generate your solution map before you ever get out your calculator or anything. All right, so go ahead and pause the video and finish the problem if you needed this hint. All right, so if you finished it, your answer would be 305 grams of aluminum sulfate. So let's go ahead and show you the solution. So we start off with 2.6 moles of sulfuric acid. We convert to moles of aluminum sulfate, right? So for every 3 moles of sulfuric acid consumed, we create 1 mole of aluminum sulfate. So that's represented in our mole-to-mole conversion here. Moles of sulfuric acid cancels, and at that point we've calculated moles of aluminum sulfate, but the question wants mass. So you need to calculate the molar mass of aluminum sulfate. I'm not doing that for you here, but if you do it on your own, you should get 342.15 grams per mole. So you multiply that on out, so you take this value, divide by 3, and multiply by this number, and you should get this value, which when you round to 3 significant figures would give you the answer, 305 grams. All right, so we've told you about these 2 tools, right? The molar masses and the information from the balanced chemical equation to solve, in general, any stoichiometry problem that you're given. The second piece of information that you need to know to apply sometimes is what's called the limiting reactant concept. So let's go ahead and focus on that part of the lesson now, and then we'll bring everything together. We'll start off with the limiting reactant concept by using a metaphor. Imagine that you're in a bicycle factory and you want to know how many bicycles it's possible to produce given the amounts shown here in the frame. So what do we have here? Well, we have 8 wheels, right? And we're adding those to 3 frames. So imagine this is a chemical reaction. Wheels is a chemical reactant. The frames is a metaphor for a chemical reactant. And we're writing an equation, right? So we have 8 wheels, 3 frames. How many bicycles can be assembled? 4 bikes? No, I don't think so, right? Why? Because you don't have enough frames, right? This is how much you can make given the amounts that are given, right? You're limited to make 3 bikes because you only have 3 frames. You have more than enough wheels. In fact, you're going to have 2 left over. 6 get used up in making the bikes. Okay, so this is a metaphor for a chemical reaction, right? We would say that the bicycle frames limit how much product we can make, in this case the bike, and so the bicycle frames are our limiting reactant. We have more wheels than we need to make our product, so they're in excess. We would call that the excess reactant. Now, why do we care about this? Because in a chemical reaction, often one of the chemical reactants will be in excess over the other. And if the question asks, how much product is it possible to be made under the experimental conditions, you have to determine which one limits how much product you can be made, just as we did in the case of the bicycles. We were limited by the number of frames. Once you identify the limiting reactant, we use that quantity to determine how much product we can make. So it's very, very important when addressing that type of question. So we're going to look at this now. Instead of a bicycle factory, let's imagine that we are in a molecular factory. And the molecular factory in question is that of making ammonia. Now, chemists need to think simultaneously at 3 different levels, right? The macroscopic level, that's the length scale of our everyday experience, and that really doesn't require much imagination. The microscopic scale, which definitely requires some imagination, right? This is the length scale of individual atoms and molecules. So that's what's being represented here, right? We have 3 hydrogen molecules, they're diatomic, and we're considering their reaction with a nitrogen molecule, which also is diatomic. And when the hydrogen and nitrogen reacts, the atoms change positions to form our new molecules, NH3 or ammonia. Now, the third way that a chemist needs to think simultaneously is symbolically, right? So the pictures that are represented here at the microscopic level, we represent them in condensed form as a balanced chemical equation, right? 3 hydrogen molecules plus 1 nitrogen molecule yields 2 ammonia molecules. This is consistent with the mass conservation law. Now, also, instead of just thinking about individual molecules here, well, we can think of sets of molecules. That's the mole concept. We can imagine that we have actually here 3 moles of hydrogen reacting with 1 mole of nitrogen to give us 2 moles of ammonia. The number relationships are the same. We're just scaling everything up by 6.022 times 10 to the 23rd. All right, so that's the background information. Now, what is this balanced chemical equation telling us? It's a recipe. it's telling us that if we want to react 1 mole of nitrogen, we need exactly 3 moles of hydrogen to do it. So that's a 3 to 1 mole ratio. That's what I'm representing here. 3 hydrogen to 1 nitrogen number ratio. Now, that's our recipe. Now let's consider an experiment where we have more than what we need for one of the reactants. In this case, we're going to take that to be hydrogen. So the question, if you look at the picture here, you ought to be able to tell that by adding more hydrogen, you're not going to make any more product. It's not possible, right? If you count all the atoms, you have 6 hydrogen atoms in the product, 2 nitrogen atoms in the product. We are limited by the amount of nitrogen we have. Adding hydrogen isn't going to help. When the chemical reaction is over, let's go back here. When the chemical reaction is over, 3 molecules of hydrogen are going to react with our 1 molecule of nitrogen to give us our 2 molecules of ammonia. And we're going to end up with a molecule of hydrogen left over, right? If we look at our experimental ratio, right, our experimental ratio is 4 to 1. And if we compare this experimental ratio with our recipe, right, what's our recipe telling us? For every mole of nitrogen consumed, we need exactly 3 moles of hydrogen to do it. When we look at our experimental ratio, we have 4 moles of hydrogen, so we have more hydrogen than we need, and therefore hydrogen is in excess. Nitrogen is limiting how much product we can make. By putting in more hydrogen, we can't make any more product. That is the essence of the limiting reactant concept. Let's look at this again, but from the perspective of adding more nitrogen this time, excess nitrogen this time. Again, our recipe, or theoretical ratio from our balanced chemical equation, doesn't change. It's always going to be 3 to 1. But now, if we add an extra molecule or mole of nitrogen, our experimental ratio is 3 to 2. And we can just look at our pictures. We can see that we're not going to make any more ammonia, right? What we're going to end up when the reaction is over is that 1 mole of nitrogen and 3 moles of hydrogen are going to react, and when they do, they're gone. And what's going to be left over is 2 moles of ammonia and 1 mole of nitrogen, right? This is the one that didn't react. So I hope you can see this from the pictures. You should also be able to figure this out from looking at the mole ratios, right? Here is our mole ratio from our recipe. This is from experiment. Now, in order to compare this ratio with this ratio, we need to simplify this. If we divide the 3 by 2 and the 2 by 2, we've simplified this to a 1.5 to 1 mole ratio, right? So again, what is this telling us? For every mole of nitrogen consumed, we need 3 moles of hydrogen to do it. In our experiment, we don't have enough hydrogen. We need 3 to 1. We don't have enough. So hydrogen limits how much product we can make. The nitrogen is in excess. Okay, so that's the limiting reactant concept. Now let's go ahead and use this in a problem. First, a bit of language. The theoretical yield is defined as the maximum amount of stuff that you can make if you're given a certain amount of reactants, right? And as we've shown you on the previous 2 slides, it's going to be defined by whichever reactant limits how much product you can make. So in order to determine the theoretical yield, you're going to need to figure out the limiting reactant first. So let's look at this by example. We're going to look at the same reaction. Hydrogen reacted with nitrogen to form ammonia, and you're asked to figure out the theoretical yield of ammonia given these relative amounts of hydrogen and nitrogen. It's given to you in moles. If they were given to you in masses, you wouldn't have to know up front that you need to convert them to moles first so you can compare the mole ratios with that of your theory. So what's the theoretical mole ratio? Well, we showed you that from the balanced chemical equation on the previous slide. It's 3 to 1 hydrogen to nitrogen. So what is it in our experiment? Well, it's 15.6 to 5.1. Now we need to simplify this so we can compare it with our recipe ratio, which is 3 to 1. So if we divide 15.6 and 5.1 by 5.1, we will simplify this to 3.06 to 1. If we compare this to 3 to 1, we can see that we have more hydrogen than we need, right? Why? Because we need exactly 3 moles of hydrogen to remove exactly 1 mole of nitrogen. And in this case, in our experiment, we have a little bit more, not much more, but more than 3. It's bigger than 3. It's 3.06. So hydrogen is excess. Nitrogen is our limiting reactant. Therefore, if you want to know how much product you can make, what limits you is the nitrogen. So we start off with the amount of nitrogen. That is the key thing in applying the limiting reactant concept here. So we start off with 5.1 moles of nitrogen. Now we need to do a mole-to-mole conversion, right? Moles of nitrogen to moles of ammonia. Look on the previous slide if you haven't written it down already. Look at the balanced chemical equation. It's giving you the mole-to-mole conversion ratio. 2 moles of ammonia are formed for every mole of nitrogen consumed. So we write it in this way, so moles of nitrogen cancels, and we get 10.2 moles of ammonia as our theoretical yield. Often the theoretical yield is reported in mass of product, so in that case you would need to multiply in a second step here by the molar mass of the product. All right, now often in a chemical reaction it's not possible to obtain as much product as what you would expect in your calculated theoretical yield. And the reason why is twofold. One, you're sloppy in the lab and you spill some of the product. So clearly the amount that you actually isolate and weigh out isn't going to be as much as you'd expect. On the other hand, you just may not be able to scrape everything out of the flask either, right? So a little bit will be left behind. But there's another reason, and that is sometimes the product that you make reacts further. One way is that the product can actually sometimes react to reform the reactants, right, in a closed loop. That is the concept of equilibrium. It's something that we'll study in the next semester. But it's also possible that the product is just reactive and goes on to form something else. And your hope is to isolate it before that happens. But that can obviously remove some of your product. So we calculate then our percent yield is a reflection of how much we actually get relative to how much we expect. So it's the actual yield that you obtain in your experiment divided by the amount we expect to get in our calculation, right, based on the relative amounts of things we have. And then to convert to percent or parts per hundred, we multiply by 100. So let's look at this by example. A student prepared 41.5 grams of bromobenzene from 25 grams of benzene and excess bromine. What was her percent yield? And you're given a balanced chemical equation, right? Benzene, 1 mole of benzene plus 1 mole of bromine reacts to give 1 mole of bromobenzene and 1 mole of hydrogen bromide, or hydrobromic acid if it's in solution. Now, let's look at the language here. The percent yield, so you have to know your definition of what that is. Well, we just showed that on the previous slide. It's the actual amount isolated divided by the theoretical yield times 100%. So the percent yield of what? You have to know what it is they're talking about. Well, you can get that from the language here. The student prepared 41.5 grams of bromobenzene. So clearly that's the thing of interest. That's our product here. And you're being told how much was actually isolated. So even though you're not told this is the actual yield, you should be able to figure out that that's what it is, right? So percent yield equals actual yield over theoretical yield. We know the actual yield. So to get the percent yield, all we need to figure out then is the theoretical yield. And again, that's the amount of stuff you can make given the amounts of reactants. So we need to know which one's a limiting reactant, right? Well, it doesn't say such and such is a limiting reactant. You have to figure that out. Well, you're told bromine is an excess. So automatically you know benzene's a limiting reactant, right? So that's where you're going to start in your calculation. Now, a word of caution here. If someone put in this question an amount of bromine, but you were told it was in excess, so I don't know, you wrote, say, 100 grams of bromine, but you were already told it was in excess, you could just ignore the 100 grams. You don't even have to use it in your calculus of thinking at all, because you know it's in excess. All right, so let's start with the information we're given, 25 grams of benzene. Here's what we're going to do. We're going to go from grams of benzene, and we're going to convert to the amount in question, bromobenzene. That will be our theoretical yield. So what do we need to do to go from here to here? Well, we need to convert mass of benzene to moles of benzene. Right? Once we have moles of benzene, we can use our balanced chemical equation. For every mole of benzene consumed, we create 1 mole of bromobenzene. So it's a 1-to-1 mole ratio. We would use that information there. And then in the final step, we take moles of bromobenzene and convert to mass of bromobenzene. So it's a 3-step process. You need the molar masses first, so that's the first thing we'll do. You calculate them in the usual fashion. And now we do the mass to mole conversion step using the molar mass of benzene. Then we do the mole to mole conversion step. It's a 1-to-1 mole conversion or 1-to-1 mole ratio. And then we convert that to mass of bromobenzene using the molar mass of bromobenzene, and we get 50.2509 grams of bromobenzene. All right, notice where I've underlined. I haven't rounded off yet because we need to use this in a further calculation. The question asks for the percent yield, right? So our percent yield is our actual yield, 41.5 grams, divided by our theoretical yield, which isn't rounded, right? We've got one more digit than we need. We're going to have to round to 3 significant figures. So we carry this one to at least one more digit. And we end up, after we round to 3 significant figures, 82.6%. All right, we're going to look at one more example. In this case, we're given 50 grams of acetylene and 100 grams of oxygen burned to produce carbon dioxide and water. You need to write a balanced equation. You need to figure out the limiting reactant. However, in most problems, particularly what you're going to see on the exam, is you might instead just be asked to calculate grams of acetylene, grams of oxygen, and grams of water that are present, say, after the reaction is complete. Now, if you think about these questions, then you should know that first of all, you're going to need to balance. You're going to need a balanced chemical equation so you can do mole-to-mole conversions. And second of all, since you're given the masses of reactants, you're going to need to figure out which one's a limiting reactant to figure out how much product you can make. So steps A and B are implied in answering any questions in C. Let's go ahead and work on A. Right? We write down the components, acetylene, C2H2, oxygen. When anybody says just oxygen, you should be thinking oxygen molecules, not oxygen atoms, because oxygen in its standard form is diatomic. It's molecular. That's something that you need to memorize. So you would write here O2. Carbon dioxide, it's a name. You have to be able to take names and write formulas, right? So carbon dioxide is CO2 and water is H2O. Now you need to balance it, right? When we look at this, oxygen is in one place here, but it's in two places here, so let's do that last. Carbon is in one place here, carbon's in one place here. So we need a stoichiometric coefficient of 2 in front of CO2 to balance the carbon. Hydrogen is already balanced, and so we just need to verify oxygen, right? So we have a total of 5 oxygen atoms on this side, 2 on this side, so we need a stoichiometric coefficient of 5 halves. 5 halves times 2 atoms per molecule gives us 5 oxygen atoms. So it's balanced with respect to oxygen. So we have a 5 halves to 1 mole ratio in our recipe, right, of oxygen to acetylene for making CO2 and water. Often what you will do is you'll remove fractions in stoichiometric coefficients. It's not necessary, but it's commonly done. Right? So we just multiply everything by 2, and we've kept the number ratios constant in our chemical equation. All right, so we've already stated that in our recipe, right, a 5 to 2 mole ratio is 2.5 to 1 oxygen to acetylene. Now, what we need to do is figure out our experimental mole ratio. So what are we given in the problem? Well, we're given masses of oxygen and acetylene. So the first thing we need to do, right, to compare with our mole ratio here to figure out the limiting reactant is that we know that we need to convert these to moles, right? Honestly, I hope that you're coming to the process that this isn't memorization, that this is stepwise rational thinking. You just know you've got to get this into moles so that you can compare the mole ratios here. So we convert these to moles using the molar masses, right? You've got to calculate them out. For oxygen, for O2, it's 32 grams per mole. For acetylene, it's roughly 26 grams per mole. So we use them to calculate moles of acetylene and moles of oxygen in the usual fashion. So now we've got 2.5 moles of oxygen and 1 mole of acetylene that's needed, right? In our recipe, in our experiment, we compare the same number ratio, oxygen to acetylene. Divide 3.125 by 1.920 on your calculator, and you'll get 1.63 to 1. So we compare this with what we have up here, 2.5 to 1. Again, listen carefully to the language. If to consume 1 mole of acetylene, what's required is exactly 2.5 moles of oxygen. If we have less than that in our experiment, then we don't have enough oxygen. And look at what we have here. We don't have 2.5 moles of oxygen available. We have less than that. So as a consequence, we're not going to be able to burn all of the acetylene. The oxygen is our limiting reactant, and when it's gone, you can't make any more product. We're going to have acetylene left over. All right, so now that we've established that oxygen is a limiting reactant, let's look at step C. How many grams of each reagent remain after the reaction is complete? Right, well, if oxygen is your limiting reactant, when the reaction is complete, you should know there's no oxygen left. There's no calculation to do, right? It's implied in understanding the limiting reactant concept that all the oxygen is gone. Let's look at acetylene. So to figure out how much acetylene is left over, first of all, you have to figure out how much acetylene is consumed. So how are you going to figure that out? Well, you can figure that out by using the limiting reactant of oxygen. The amount of oxygen that's consumed dictates how much acetylene is consumed, right? By looking at the balanced chemical equation, right? They react in a 2.5 to 1 oxygen to acetylene mole ratio. So we use our limiting reactant to figure out how much acetylene is consumed. We use our mole-to-mole conversion. 5 moles of oxygen for every 2 moles of acetylene, and we use the molar mass of acetylene to give us the the mass of acetylene. So, what have we calculated here? Is this the amount remaining? No, it's the amount consumed, right? To get the amount of acetylene that remains, we need to take the amount that we started with, which was 50 grams, subtract the amount of acetylene that was consumed in the reaction, and then what you're left with is the excess. That's what's remaining. Keeping track of our significant figures, right? The uncertainties in the tenths place, we would round to 14.5 grams. Sorry, 17.5 grams. All right, the last part is to calculate the amount of water that's formed in the reaction. So this would be analogous to the theoretical yield, right? So where do we start in the calculation? You start from the limiting reactant. It limits how much product you can make. We need to know the molar mass for water. So we take our limiting reactant, moles of oxygen, we convert to moles of water formed, right, using our balanced chemical equation. It's a 2 to 5 mole ratio. We multiply by the molar mass of water, and we get the mass of water that's formed. And yes, that's going to be the amount remaining after the reaction's completed. Okay, go ahead and go ahead and pause the video and see if you can do this problem on your own. It's a percent yield problem. You're going to need to figure out the limiting reactant in this case. All right, so again, the percent yield is what you need to figure out. Percent yield is actual yield over theoretical yield. You're given the actual yield here. So you need to figure out the theoretical yield, right? So the theoretical yield is the amount of sodium chlorate that's possible to be made given these amounts of chlorine and sodium hydroxide. So these are the reactants. Now you need to use a limiting reactant concept here because you don't know which one of these limits how much of the product you can make. So we need to do that. The answer is going to be 47.3%. And now let's show you why. Look at the balanced chemical equation, right? Sodium hydroxide and chlorine react in a 6 to 3, that's a 2 to 1 mole ratio. Now, what are we given in our experiment? We want to compare the same mole ratio, sodium hydroxide to chlorine. So we take 1.49 moles of sodium hydroxide, divide by our 4.25 moles of chlorine in our calculator, and we'll get roughly 0.35 moles of sodium hydroxide are present for every mole of chlorine present in our sample. Now when we compare, again, what is our recipe telling us? If we want to remove a mole of chlorine, we need at least 2 moles of sodium hydroxide to do it. Do we have 2 moles of sodium hydroxide present? No. So the sodium hydroxide is our limiting reactant. We're going to have chlorine in excess. When the reaction is over, we'll have chlorine left over. So in order to figure out the theoretical yield of sodium chlorate, that is the amount of sodium chlorate you can make, you use the limiting reactant, which is 1.49 moles of sodium hydroxide. We use our mole-to-mole conversion, which is 1 mole of sodium chlorate produced for every 6 moles of sodium hydroxide consumed. So that's shown here. Then we use the molar mass of sodium chlorate that you calculate on your own. You should get this value. And we get this mass of sodium chlorate, right? So this is where we would round if we were going to do that at 3 significant figures. But we don't do it yet because we need to calculate percent yield, which is actual yield, over the theoretical yield. This is our theoretical yield. So we take 12.5 grams, divide it by this, and then round to 3 places, and you get 47.3%. And we're finished with this chapter. Take a deep breath. I hope you found this useful. Please let me know if this was helpful for you.